Hello and welcome to Pearson's R and Spearman's Rho. We're going to look at inferential statistics that help us establish whether or not a correlation is significant. As you can see from the spec, the two we have to know are Pearson's R and Spearman's Rho. Spearman's Rho is often referred to as Spearman's rank, and you may have covered this in biology or other related disciplines. Pearson's R correlation, our first test. Now this is a parametric test, and just to remind you what parametric means, it is a test that uses a safe measure, a measure that we can agree on, something that is unambiguous, and the data that we use in our test is going to be relatively raw, so we haven't done anything with it. We haven't ranked it or modified it really. When do you use it then? When the hypothesis states a correlation between two sets of data, when two sets of data are related, i.e. they're paired scores, usually from the same person, when the data fit the requirement of the parametric test, so in other words, data at interval, the population is assumed to have a normal distribution, and variance of the samples is assumed to be the same. An example might be, there is a positive correlation between the length of time in weeks taking SSRIs and the reduction in resting heart rate. So the covariables in this study would be length of time measured in weeks. Weeks is a safe measure. Weeks is universally acknowledged, at least in the scientific world, as consistent of 7 days. 7 days have an objective meaning, and therefore this is quite a safe measure. No one's going to say, what do you mean by a week? We know what a week is. Heart rate equally is a safe measurement. So this is how we carry out a Pearson's correlation. We state our hypothesis. Remember, it has to be correlational, so if it was a directional hypothesis, it would say X and Y are positively correlated or negatively correlated, or if it's a two-tailed hypothesis, you might say there is a relationship between X and Y, but you're not stating the direction. Step 2, we place the raw data in the table. I've done this for you. So we have to calculate X squared for each value in the X column and Y squared for each value in the Y column. Once we've done that, we multiply X and Y, so in this case 4 times 2, and produce the answer there. So 4 squared is going to be 16, 2 squared is going to be 4, and so forth. And X times Y is going to be 4 times 2, so that'll be 8. Fill in those columns, and then once you've done it, for each column you sum it. You add up all the numbers. So sum X equals that plus that plus that plus that plus that, all put in this little equation here. Sum X squared, everything in this column, and so forth. So this is what your data should look like. I've gone through and squared all the values. I have the sum of X here, which is 340. The sum of X squared, the sum of Y squared, and the sum of X times Y. And I've produced it in this little chart down here. Now this is the Pearson's R correlation. It's one of the ugliest correlation equations that you're going to see in psychology. But it is actually not as complicated as it appears if you take it very step by step, one equation at a time. So in this case, I quite like working out the bottom first. It just feels a bit more correct. So if you see, we've got n times sum X squared. So n refers to the number of participants or sets of data. In this case, we have 10. So this could be a nice easy equation. Sum X squared is this number here, sum X squared, and that's 17108. So the first part we do is we take 10 and we multiply it by this number here, 17108, and that gives us 17108.0. We then calculate this score, which is 340 squared, which produces this value here. 115,600. So we then take this number and subtract that number, and that will give us a total. So that's what it looks like, 171,080, and we're going to subtract 115,600 from it, and that produces 55,480. So we can just place that down there, 55,480. So that's the sum of this equation here. Then we've got 2910. Remember, we got this from taking 10 and multiplying it by the sum of y squared. So y squared is 291. We multiply that by 10 to get 2910. So now we take 2910 and we subtract from it this sum here, which works out as 2401. And that gives us 509. The next step is to multiply, because these are right next to each other, this number by this number. And that produces this big beast of a number, 282,39320, and we square root it to get 5314.1 if you want to be precise, or 0.07. So 5134, that's absolutely correct. Now the top row you should be able to calculate for yourself. So I would remember your bid mass. So multiplication comes first, multiply these two, and then subtract whatever the sum of that is from this, and that gives us this value here, 3930. You divide that by 5314. We get a Pearson's R of 0.740. Now, remember, the closer a correlation is to 1, the stronger it is. So this looks pretty strong. This looks like our study, which in this case was the number of weeks using SSRIs and the reduction in heart rate, is significant. There is a relationship, and because it is a plus number and not a minus number, there is a positive correlation. In other words, as the number of weeks using SSRIs continues, so too does the reduction in oh no, sorry, yeah, I'm confusing myself. So the weeks go up, so does the reduction in heart rate increase. So we're talking about an increase in the reduction, so that's a bit confusing. Poor wording in that case, but you get the idea. So that's how we carry out a Pearson's R. This is the worst possible equation they could give you in the exam. It's very unlikely they would do it. They'll probably give you a Spearman's, and we'll have a look at that in a minute. But now we've got our value, 0.740, we need to see if it's significant. So to work out the degrees of freedom, we take n, which is 10, subtract 2 from it. This gives us a degrees of freedom of 8. We're using a 0.05 because no one specified otherwise. So we find the critical value, which in this case is 0.549. Does Pearson's R have a R in the title? Yes, it does. We use our greater rule, and therefore our R value, our calculated value or observed value, is greater than our critical value. Therefore, the result is significant. We reject the null hypothesis, accept the alternative hypothesis, suggesting that the number of weeks using SSRIs and reduction in heart rate are correlated or positively correlated, depending on what your hypothesis was. Cool, Pearson's R. That one's tricky. That's pretty much the hardest one you'll look at next to the t-tests. Compared to it, the non-parametric Spearman's is a walk in the park. So let's have a go at Spearman's. When do you use the test? Well, if a hypothesis states a difference between two sets of data, data are paired scores from separate groups of participants, when one or both of the covariables can be treated as ordinal. Height and attractiveness. Now, height is actually interval data, but it can be treated as ordinal if you, for example, order people by their height. But this one definitely is. So attractiveness score is definitely going to be ordinal. That is not a safe measurement. That is not obvious what a score of 5 means. 5 out of 10, what does that even mean? So the procedure, I think you're getting the hang of this by now. You state the hypothesis. There is a positive correlation between height and attractiveness. Though it's worth noting that the relationship is likely to be curvilinear. And what I mean by that is as someone gets taller, they will be seen as more attractive, but surely there's a point where, you know, tall is too tall. And actually, you know, 8 foot, not necessarily 9 foot, but, you know, with sort of, maybe not curvilinear, but yeah, definitely an odd correlation where it tails off. Anyway, no, curvilinear, if you could get people that tall. So let me explain what I mean. So curvilinear, you know, as height goes up, you know, 4 foot, 5 foot, 6 foot, when we get to here, like 6.5 feet, this is maybe the peak of attractiveness, and then we get 7 foot, 8 foot, and then world's tallest man. So that's what I mean by curvilinear. Anyway, let's ignore that. We're looking at a linear relationship between height and attractiveness. So we have two values. We place the data in the table. We have our height, and we have our median attractiveness score. So this is a score out of 10. What we have to do as Spearman's row, and sometimes referred to as Spearman's rank, is that we have to rank these. So we find the smallest value here, which I think is 166, and that becomes number 1. The next smallest value is 167, that becomes number 2, and so forth. By now you know what happens if you have two values that are the same. So if you have two values that are the same, you add their ranks together and divide them by 2. So in other words, you calculate the mean for that rank. You do the same here. So we find the lowest attractiveness scale, which is, I think, 4. Yep, 4. So 4 becomes number 1. However, here we have 5, which would be number 2, 5, which would be number 3, 5, which would be number 4, and 5, which would be number 5. Now, 2 plus 3 plus 4 plus 5 divided by 4 makes 3.5. So this rank is 3.5, this rank is 3.5, this rank is 3.5 and 3.5. That means that the next rank has to jump and has to be at number 6, rank number 6. So this is our table completely filled in. I've gone through and ranked them all. As you can see, the ranks 3.5 that we pointed out earlier, they're all in order, or they're all ranked, I should say. We've then calculated the difference between the ranks and squared the difference. And that gives us this value down here. And that literally means the sum of d squared, which adds up, when we add up all these values, to 245. We then plot that in our equation. Compare this to the Pearson's equation. This is a work of art, simplicity and beauty. So to calculate rho, we take 1 and subtract from it 6 times this number here, 245, over n, which is, remember, the number of sets of data, which is 13, over n times n squared minus 1. So this is it passed out, and then these are the values that we wind up with. So 6 times 245 equals 1470. 13 times 168. 168, by the way, is 13 times 13 minus 1. That gives us this value here, and that produces a row value of 0.33. You don't really need the 0, but 0.33. It's a positive value, and as you can see, if 1 is a perfect correlation, 0.33 is a relatively weak one. But if the sample size is big enough, it may still be significant. So let's find out if it's significant. 0.33, we have 13 participants at a one-tailed hypothesis at a critical significance level of 0.05. We need to meet or exceed, that should say Spearman, sorry. We need to meet or exceed 0.484. In this case, our value does not meet or exceed. It is not greater, Spearman's greater, than 0.484. So we accept the null, we reject the alternative, and all that good stuff. Now, it's worth noting that if we just had, let's zoom down here. If we had 25 participants, we would be very close. If we had 25 participants and produced that value, I bet if we had 26 and produced that value, this would be a significant result. This shows you how the threshold, the smaller the number of participants you have, the higher the correlation needs to be significant. But the more participants you have, the smaller the correlation has to be to meet that critical value. And it's really important that actually you understand that this is where a lot of correlations come from in the media. They come from using these huge sample size, 10,000 people, and they produce this tiny little correlation. But because the number of participants taking part is so large, it means that they often find results, many of which actually happen to be erroneous correlations or type 1 errors. And that's why you can produce garbage like this. Spurious correlation, margarine linked to divorce. Look, a 99% correlation between margarine and divorce. So watch out. So those are the two inferential statistical tests you need to know to calculate correlations. We've done Spearman's row and Pearson's R. Remember the main reasons why you would choose either. In the exam you could get a 3 marker on this. Why would you choose the Spearman's for a study? Why would you choose the Pearson's? You need to know those reasons. We're going to put together a mnemonic that will help you remember it, but that is all you're required to do for now. Make sure you've calculated and had a go at each of those equations and check your answers. As always, thank you very much for listening, and I will see you next time. Goodbye.